All right, so instead of just going through the PowerPoint, I mean, you have what you have in the notes is essentially what you did with the matrix multiplication in the Excel boot camp. So I don't know if you noticed that, but it's just a review of the matrix multiplication. I wanted everyone to go through this themselves, and in the past, I actually had you guys build the HD workbook. And then when you got to the discussion questions, many times you weren't able to answer the question. So that told me you didn't really follow along with what was meant by what you were doing. You were following the instructions right, or you in general, as students, were following the instructions correctly, but it wasn't really engaging the brain as to what was happening. So we've already looked at the particle in a box system, and you've solved the Schrodinger equation and the transition dipole moment integral and simulated the spectrum by hand using analytical methods. That was kind of a pain. I mean, do you agree? I mean, the calculus was, how many pages was your set of equations? Yeah, very long, basically. Then we did the symmetry, and just doing the symmetries of the three wave functions in the transition dipole moment integral, you could do that on a post-it note. So we can take 4 pages of calculus, reduce it to a post-it note, but what do you lose? You lose the actual intensity. All you get is 0 or non-zero. Okay, so what we're doing next week's lab, and I'm going to go over today in detail, is we're going to do it numerically. So in terms of taking the derivative by hand, that's kind of a pain, right? Sometimes you have to do trig substitutions, and then you got to remember that the derivative of sine is cosine and all of that. So you got to do all that by hand. Taking the derivative in Excel is just rise over run. So it's just the slope. We know the derivative is the slope. Well, in Excel, you can just take, the y value for the previous data point and subtract the y value for the next data point, and that's the difference in rise. And then you can take the x values and take the difference of them, and that's the run. And you're taking the derivative. And then you just copy that formula down, and you've taken the derivative of the wave function. So it can't be easier just doing it by hand. But I say by hand, but we're really using Excel. So we're not doing it analytically by hand, but we are doing it numerically by hand. So whenever you hear numerical analysis, think tables, right? Tables of numbers. And so computers are really fast. That's what Gaussian is doing. We kind of, in the past, would have had the numerical analysis lab be this week and the Gaussian next week. But at the end of next week is your lab. So I wanted that Gaussian, since it's on the is the exam. Since Gaussian's questions are on the exam, I wanted that lab experience to be this week. So the numerical analysis is next week. It's also on the exam, but the questions are a little easier than the Gaussian. Okay, so we're gonna go through this, but I'm not gonna really go through the PowerPoint as much as I'm just gonna bring up the Excel spreadsheet. So y'all in the back may want to scoot forward, because I can expand the font so much, but not so much that you can see it in the back. So go ahead and come on forward so you can see the spreadsheet. It'll really help you next week. So I'm working through pretty much next week's lab today in class. Okay, so let's jump in. So let me just work with my screen here. Yeah, there we go. So this is the numerical approach to the quantum mechanics of the 1D particle in a box system. So what we're doing is we're simulating the spectrum of a particle in a box. And we're going to do this in a smaller table so that you can see it. In the past, like I said, I had you do the high definition version, which had 200 rows in the table. Well, it's hard to see what's happening with 200 full rows. But here, I just have you have 10 rows in your table. So first of all, it's a particle in a box. So let's pick the size of the box. So here I'm picking 8. Oh, that's not up there. Thank you. Let's go with... Make sure that I see what you see. So. Okay. There we go. Now you can see it. All right, very good. So we picked the pick the box length here at 7 angstroms. Or 8 angstroms. We're gonna do the mass of an electron, just like you did in all of your lab experiences. And so, if you go through the lab next week, you'll see you have very clear tasks to do. So, like for the very first task is we're going to plot the wave functions. Here's the mathematical formula, and you've got to figure out how to put that into Excel. And so to do that, you're going to want to anchor cells, like the L needs to be anchored up there at 8, and so on. So we go down here, and you see I've got it filled out. Yours that you get on Monday or Wednesday or Thursday, whenever your lab is going to be blank here. So you've got to put in the formulas for the particle in the box. So let me just go ahead and look at that. If I click here, you'll see that it's color-coded. So if I scroll up, you see there's the box length. It's in blue, okay? And look at the anchoring. It's got $signs in front of the column and in front of the row, and that anchors it up there so that when I copy it over and copy it down, it still refers to L. But if you look at the X anchoring, in pi X, okay, that's the purple cell. It's just got a $sign in front of the column, the letter. That's never happened before. Okay. And a very handy thing is to use F4 to cycle through the anchoring of the column or the row and so on. So then on this spreadsheet, we've got them plotted down here. So you can play around with the quantum numbers. So I'm plotting 1 and 2. Let's plot 1 and 3. So you can change. All of the gold colored cells are ones that you can change and play with, okay? And so here are the wave functions. You see psi 1 is in blue, psi 3 is in orange. Why is it so choppy? Because we only have 10 rows in our table. Now, this is an important concept, so everyone wants you to pay attention. The fineness of the grid, that phrase, the fineness of the grid, is important in numerical analysis. So fineness, F-I-N-E-N-E-S-S, fineness. So it's how many intervals you have your system chopped into. So we only have chopped our system into 10 intervals. That's pretty coarse. So it's not fine, it's coarse. If you want accurate results numerically, you need a fine grid. A coarse grid is going to give you lots of errors, okay? Because if you think about doing an integral of a function, you're making rectangles out of all of these. It's the y value times the delta x value. If delta x is big, then I've got this area here that's not under my curve that I'm counting when I take the area there. And so the more coarse the grid, the more of those corners of those rectangles that I'm adding up to make an integral are included or excluded. And so those are the reasons why numerical integration and differentiation are not as accurate if you have a coarse grid than if you have a fine grid. Okay, so we build the two wave functions here. We then square them to see if they're normalized. And when we square them and integrate them, we see we get 1. And when we multiply wave function, n versus wave function n prime and integrate over all space, we should get 0. And so we're showing that they're orthogonal. I have you go through multiple ways to do numerical integration in Excel. So you can make new columns where you square them, and then you can sum those columns. That's the slow way to do it. Or you can do like sum product, where you just have this function that squares each cell and then sums them together all in one shot. So that's a second way to do it. And then times dx, so that's your integral, okay? Or then you can use matrix multiplication. So this one over here is matrix multiplication. And you can see inside this matrix this M-mult, transpose, and so on. And we'll explain what the transpose is doing in the lab next week. But essentially, it's taking this block of wave functions here, turning them sideways, and then multiplying them by that same block, so that the top row times the first column added together will give you this top cell here. So this is what we see in orthonormality, and this is the Kronecker delta. When the n is equal to n prime, the integral is 1. When n is not equal to n prime, the integral is 0. You can change this around. You could put 2 here, and you still see the same result. So the first 5 tasks are just the wave functions and showing that they're orthogonal and normal. So our normalization constant of the square root of 2 over L is working. It's normalized all of our wave functions. And so that's just working with the wave functions and introducing numerical integration. So then we also are able to look at the symmetries of these wave functions. So this is kind of cool. So look here, this says it's even. Well, how would I know, like, how do I determine if it's even? It's an if-then statement. So look at where 0 is in column B. So I'm going left one row and looking at the value, and I'm comparing it to if I go right 1 row. So left and right being if it's the x-axis, I'm going left and right on the x-axis and looking at the cell values. If they're the same cell value, then it's an even function. So that's what this if-then statement is. And I've already programmed this if-then statement in there just so you could look at it, though, and see how it's done. So if C19 equals C21, then it's an even function. If C19 is equal to negative C21, then it's an odd function. Otherwise, it's NA. So if I have some other function that's neither even nor odd, then it would just give a not applicable. So we can see that the first wave function is even. This one says it's odd, which matches this logic here, because they're the same value but opposite sign. And so it's just an even odd test. So we have the symmetry on this page too. And so an even times an odd function, integrated over all space, should give you 0. And that's what we see with the Kronecker delta, that 1 times 3 or 1 times 2 integrated over all space is 0. So anyway, that's a little bit about the wave functions. Here are the plots of the wave functions. And here are the plots of the wave function products. So just for curiosity's sake. Okay. And you can see that this orange curve is wave function 1 times wave function 2. And you see, yeah, there's some positive regions and some negative regions. And when you integrate over all space, the integral is 0. Okay, so those are the first 5 tasks. Let's go up now and solve the Schrodinger equation. Up here we have some constants. Notice I have Planck's constant written a couple of different ways. One is in angstroms squared in kilograms, and the other one is in kilojoules. I do that just so that it can convert the box length in angstroms over using Planck's constant, and Avogadro's number. So task 6 is to expand the x-axis. So what are we doing here? Notice that our box length is 8 angstroms. So we're centered on 0, so it goes from -4 to +4. So you can see that here in this black box. And so whenever we take the slope, it's rise over run. So we have a bunch of different ways to do that. Sorry, my phone is acting up. Let me just do it on Excel. So if we were to look at this plot and I wanted to take the slope, I've got this value here. Can you see my mouse? Okay. I've got this value here, and I could subtract that value. So that gives me the slope there. And then I could divide by the x increment, and that gives me the slope. But where do I put that result? If I put that result right here on 4, okay, that's fine. But then when I get over here to this 4, +4, I don't have a number to calculate the slope at this point because there's no more numbers on the right. You see, I'm doing forward derivatives. I'm looking at the next point minus the current point and plotting the slope at this point here. So I can't go forward once I hit the end of the box. And what that does is that it shifts the slope, the symmetry of the wave function. So when I'm right here at 0, the slope I'm going to plot at 0 is this number minus the number at 0. Well, that's going to give me a positive slope at 0. But if you look at 0, the slope is 0 at 0. So it's going to be inaccurate. So how do I get accurate slopes, the derivative? And how do I have a number when I hit the end of the box so that I can actually calculate it at the end of the box? I've got to go past the end of the box a little bit. So that's why we have to expand the box a little bit. Now, what I would like to do is, instead of calculating the rise over run, like let's sit right here at 0, instead of calculating this forward one minus the current one, what I'm going to do is I'm going to take the forward data point and subtract the one behind me, and then divide by 2x increments, and then plot that right at 0. So do you see how that's accurate then? The one forward and the one behind will give me a slope of 0 at 0. Because this point right here and that point have the same value. And so when I plot that difference and divide by 2x increments, then I plot that slope right here at 0, then the slope in the center of the box is 0, which preserves the symmetry of the function. So what we call that's called centered derivatives. We could have forward derivatives, which is what I was talking about. If I'm going to plot the slope at 0 and I just take this first difference here, this one minus this one, I'm looking forward. I could do backwards derivatives, and a backward derivative would allow me to calculate the derivative at this end of the box, but I wouldn't be able to calculate it at that end of the box because there's nothing behind that data point. So centered derivatives preserves the symmetry of the function. And so that's what we're calculating in this group. So I can't calculate the derivative at either end of the box because I don't have anything on either end beyond the end of the box. So we have to expand the box 2 cells or 2x increments so that I can calculate the first derivative and the second derivative. So when we're doing the Schrodinger equation, we have to calculate the second derivative because that's the energy. So this is why we expand the box on both ends. So you see this goes from -4 to -4.8 to -5.6. Okay. And then up here it goes from 4 to 4.8 to 5.6. So we're going beyond both ends of the box just so we can calculate those derivatives. And we can do that mathematically. It's not a problem. But we still want to have a visual reference as to where the box actually ends. And that's, minus L/2 to L/2. So here's our psi prime, our psi for n and psi for n prime, and then the derivatives, the first derivative. So let me show you this function. You see how it's the centered derivative. It's the forward y value minus the backwards y value divided by the forward x value minus the backwards x value plotted at that point. Okay. And so when we plot it at that point, that's the formula for this cell right here. And then we've lost that cell. So we just calculate it from here down. And then we do it again here, and that's the second derivative. So psi double prime, let me double click on that one. You see it's the rise, the derivative of this psi prime. So it's the forward minus the backwards value divided by the forward x minus the backwards x. So those are the first and second derivatives. Can you believe how easy that is to calculate first and second derivatives numerically? It's just the slope. There's a little funny business with the centered derivatives, but still it's understandable, right? Forwards minus backwards plotted at that data point. That preserves the symmetry. And so still, that's a whole lot easier than remembering my trigonometric substitutions, right? So that's very nice. So we've taken the first and second derivative. We can plot those. So remember for the wave function for psi, let's just look at the blue curve. You see it's a sine function. And so what's the slope of that blue curve? It's coming right out of the end of the box with a slope of 1. That's cosine. So we should see it should look like a cosine, and it does. It looks like a cosine right here. Okay. And then when we take the slope of that one, okay, we get minus sine. So exactly what we would do analytically, that the derivative of sine is cosine and the derivative of cosine is minus sine. And so that's what we have. Okay. And then we can take the integral of that second derivative and multiply by all those constants and get our energy for the Schrodinger equation for the particle in a box. And we end up with 55 kilojoules per mole. Now look at that. This is the analytical solution. So this one is using the analytical equation of n squared h squared over 8ml squared. That's the actual result for the energies of the particle in a box. Okay. So this is our true value, our known, and this is our estimate, our numerical estimate. And it's pretty good for the ground state, 55 versus 56. So 3% error, we're 3% low. Okay. And what we're doing when we integrate, again, we're taking that curve and we're breaking it into kind of like a column graph and adding up the areas of those columns, right? It's the y value, the sum of the y values times delta x. So we're getting the area under the curve. The more complex the function, the more error there is. So for the next wave function, I think do we have n equals 3 or n equals 2? Let's go all the way back over there and look. 2, okay. So n equals 2. Let's look at the error we have. 12% error for n equals 2. Okay. What about n equals 3? Okay. Let's see if I can do some freeze panes here, and we'll. All right, so all right, let's go down. Okay, so this is a handy skill that you need to know someday, is this ability to freeze the panes. Here, freeze panes. If I click freeze panes, then watch, I can scoot to the right and the 1 and 2 will stay there. Okay. So here's our error analysis of our numerical results and our analytical results. So if I change this to 3, okay, then our error, why did they not do? It's making a liar of me. Oh, here, change this one. That's it. 3. So 26% error. Okay. So it gets bad fast, and that's because our grid is really coarse. We only have 10 increments in our box. Okay. You'll see that it's much better on what I call the high definition spreadsheet. Okay, so that's the Schrodinger equation. Let me unfreeze those panes. And now we need to look for the selection rules. So we'll recompute the wave functions. Okay. We don't need to expand the box because we're not taking derivatives. Okay. What we're going to do now is we're going to perturb the wave functions by multiplying by the electric field of light. So we're going to create psi and x times psi. So this is the wave function. Okay, we've already seen that function. Look at x psi. So remember, the transition dipole moment integral is the angle brackets for Dirac notation, and it has the wave function times x times the wave function. So we're going to left multiply that first wave function by x, so x psi. We're going to make that. And so we can see that formula is just the x-axis times the wave function. So in that transition dipole moment integral, that's all we have, x times the wave function. Okay. And so that's x times wave function 1. Here's wave function 2. Okay, same thing, x times wave function 2. We're going to use the integrals to integrate that over all space. And so here's our 1 to 2 transition. So that's fantastic. That's the transition dipole moment integral. And we did it real easily with M-molt. We took the wave function times light times the wave function, integrated over all space, and there's our result right there. So we know it's non-zero because you can see it right there, 2.07. Okay, and that took many, many pages of math to do by hand. Okay. Now you might say, well, this is many, many pages in the spreadsheet. It's a whole lot easier to just double click that little box in the bottom corner and have it paste down, right? Than it is to start writing all of your equations over and over again. Okay, so let's look at some of the transitions that are not allowed. Okay, so 1 to 2 is allowed. What's the delta n for a 1 to 2 transition? Delta n equals 1. Okay, let's go to 1 to 3. Look at that, it's not allowed, 0 and 0. Okay, you see a number here and you go, but it's non-zero. Well, that's times 10 to the minus 39. That's Excel telling you it's 0. Okay, it's again those numerical errors, but on this one, that's actually the tolerances of Excel. That's as close as Excel gets to 0 with the little numerical errors built in. So Excel, it's just the math isn't all canceling out numerically for the CPU and however it's calculating those differences. Okay, but for our purposes, something that small would be 0. Okay, and then let's go 1 to 4. Okay, non-zero. So a delta n equals 3 would be allowed. Okay, and then what about 1 to 5? So this is a delta n of 4. Again, 0 to 5 decimal places. It's 10 to the minus 32, but that's 0. Okay. 1 to 6, allowed or not? Allowed because that's delta n equals 5. Yeah. Really, really small, but still non-zero. Okay. And again, it would match our functions, odd and even and so on, but these are NAs because they're crazy. Okay. All right, so we have solve the transition moment integral, and by playing around with it, 1 to 2, 1 to 3, 1 to 4, 1 to 5, we were able to get the selection rules. What about a hot band? Tell me what I could put in here to get a hot band. 2 to 3. All right, 2 to 3. So again, allowed. Okay, so that's fantastic. That's the other nice thing about viewing this numerically in an Excel, because you can get in, then you can play with it. You've built a dynamic sheet and you can see what transition intensity would be for a 5 to 6 transition or whatever. Okay. So now let's go over here to the last task. We've solved the selection rules. Let's plot the simulated spectrum of the transition. Again, we got some more constants up here. We've got the energy of the ground state, so we could use that in the Boltzmann distribution calculation. First task is to compute the transition wavelength. So these are anchored. These quantum states are, let me just scoot over so we can see it, anchored to AD13 and AE13. So that's these over here, AE and AD. So these down here, the ones we were just playing with. So we're doing the fundamental transition from 1 to 2. So this is the upper state is 2, the lower state is 1. Here's the energy of the upper state, the energy of the lower state, and then this is the spectral line. So this is, once again, I want to emphasize that the spectral line is a difference between energy levels. So we're going from 1 to 2. So that energy difference is delta E, and that's what you convert to wavelength. Okay. So some people get confused, so they'll take the upper state and they'll convert that energy level to wavelength, and that doesn't make any sense, because light is causing a difference, causing the electron to jump from state 1 to state 2. So that's the energy, that energy difference. The delta E is what you convert over to wavelength. So here's the delta E, that's the spectral line, and then converting that to wavelength using Planck's constant. So that's the transition equation. And then we have the Boltzmann factor. So this is the probability of being in that energy level. Now, this is the fundamental, so 1 to 2. So we have a 100% chance of having molecules in the ground state, okay? And it's temperature dependent. This is the temperature here. So no matter what I do with the temperature, this probability is not going to change. So like even if I made it room temperature, 300 Kelvin, okay, no change. We'll do a hot band in a minute, and then we'll see a change. So I'm going to undo that. Here's the TDM integral result. So this is the intensity. So remember, the absorption profile is big. Boltzmann, the integral, and the Gaussian. So the Boltzmann is this piece right here. Okay. This is the integral piece, the transition dipole moment integral. And then this is the Boltzmann. So this is the width of the Boltzmann peak. So the spectral line shape has got a width to it. And so I've got to plot that. So this is all of these, the Boltzmann values plotted all the way down. So we're plotting that whole spectrum. This is the horizontal axis of the spectrum. This is the vertical axis of the spectrum. I wanted a smooth curve, so I did a whole bunch of rows. Okay. So here's our spectrum. So that's the intensity of the fundamental. It's centered at 700 nanometers. It's got a Boltzmann width of whatever I said, like 50 nanometers. The intensity is that transition dipole moment integral. So we did the whole thing. Now, by hand, y'all did a stick spectrum because I wasn't going to make you calculate the intensity of the Gaussian at every data point. You'd have to do 1,000 of those calculations. Okay, but you can do a stick spectrum. You can just take the Boltzmann times the integral intensity. So let's play with it now. Okay, let's make a higher resolution instrument. So look at this 0.016, and we can see it almost goes, the width almost goes to 800 and down to 600. Let's make it a really low resolution instrument, 100 nanometer wavelength. See how wide the peak is? It's still centered at 700, but it's a really fat peak. So in a spectrum, if you're in instrumental analysis, this would be like having the slits on the experiment really wide. So it's letting lots of light through. Okay. What if we go narrow? And also look, it's a shorter peak because the area under that curve is the same. So as it gets wider, it gets shorter. Let's go up to like 20. So it should be really narrow and tall. Okay. So that's there is a natural line width, but most of our line widths in spectroscopy that you're going to deal with on regular spectrometers is going to be instrumental based. So this is the resolution of our instrument. So if we have a high resolution instrument, we're going to get tall peaks with narrow widths. If we have a really poor instrument with low resolution, we're going to get low peaks with wide widths. Let's look at the hot band. So let's do 2 to 3. Still allowed. Okay. We still have a peak. Now the 1 to 2 is at 700 nanometers. Now the 2 to 3, it goes up as n squared, and so this is a bigger difference. Longer arrow, which means a shorter wavelength. So sure enough, this is almost 400 nanometers. That's where that peak is. But it's a hot band, so let's cool it down. So I have it 500,000 Kelvin, just because in order to get the wavelengths in the visible region, I needed really energy levels that are really far apart. Okay, so that the arrows would be really long, and we'd have short wavelength peaks in the visible region. Well, if the energy levels are really far apart, I've got to really heat the electrons up to get them in the excited states. So let's drop this from 500,000 to 50,000. And what I want you to do is look at this. This is the probability of being in that energy level. So right now we have a 96% probability of being in that energy level. If I make it 50,000 Kelvin, it drops to 66% chance. If we were looking at this intensity, it's now 0.03 roughly. So let's make it 5,000. 2% chance. And the intensity is not 0.03, but now 0.0008. Okay. So that's why this is a hot band. Let's make it room temperature. 300. 0. Okay. Now you still see a peak, but it's 1 times 10 to the minus 31. So there's just not any molecules in that second excited state, so they can't go from 2 to 3 if there aren't any in 2. So we cooled it down, everything's in the ground state. So how do we know if it's in the ground state? Let's go back and change our quantum numbers to 1, 1 to 2. Okay, so now we're back doing the fundamental. 300 Kelvin, big peak, right? Still 100% chance of being in the ground state. That's one of your tasks down here. I think there's different questions. You'll in this week's lab, you'll answer in the spreadsheet. So you'll type your answers into these cells, and then you'll just upload the spreadsheet, and the TAs will grade your spreadsheet. Okay, so your answers will all be in the spreadsheet. You won't have an extra Word document. I think that makes it convenient for you. You're playing around with it. You can write your answers right there in the cells, and so that's great. So it's talking about changing the temperature, changing the box length. Then we'll look at the high definition workbook here in a second. So let's change the box length and see what happens. Okay, so we've got the fundamental. It's centered at 700. Let's see, I'm going to shrink this down a little bit and try to do the freeze page thing again, because the box length is way the heck over here. Okay. Oops, too far. All right, so I'm going to freeze this pane right here. Okay, so now when we go over here to the right, we can see the box length. See how convenient that is? So here's our spectrum. Let's see if I can. All right, so here we are with a box length of 8. Our fundamental is centered around 700 nanometers. Now, box length is in the denominator of the energy equation. So if I make the box length bigger, the energy levels crush down, they drop. And also the differences drop. So if the differences between the energy levels get smaller, what does that do to the wavelength? Smaller arrows mean longer or shorter? Longer wavelength. So let's test it. Now, don't get crazy, because it will be hard to see quickly what happens. So just go to like 8.1. 8.1, maybe that's too small. But did you see it? So let me do undo. See? And redo. So that's 8.1. That's 8. 8.1. 8. So that's pretty cool. I mean, think about that. It's very sensitive to box length because it's L squared in the denominator. Now, this is what we're doing in the spectroscopy course. So this is really the last time we're going to fiddle around with a particle in a box. And yay, I can hear you. Okay, but what the concepts are is if I can measure the center of this peak, I can know something about the size of the molecule. You catch that? We're coming at this from first principles. We're starting with our model, the box, and we're simulating the spectrum. In reality, you're going to go into the lab, you're going to measure a spectrum, and you're going to peak pick. You're going to find the center of this peak, and then you're going to work backwards to learn something about the molecule. So the bond length in carbon monoxide is related to the center of those peaks. You find the center of the peaks and solve for the bond length of carbon monoxide. So we're doing it, again, from first principles, so we have control of everything. We're doing it with the wave functions even. You're going to be taking the energy equations for rotational motion, and you're going to solve for the center of those peaks. you're going to do a linear regression so that you get good statistics. You're going to have like 50 different peaks, all related to the size of that molecule, and then you're going to solve for the size of the molecule. So it's exactly related to this. Okay. We've looked at the temperature effects by fiddling with the Boltzmann distribution, and we can see the hot bands go away and the fundamental doesn't. Now in infrared spectroscopy, all you're looking at is fundamentals. Now in the rotational spectrum, you have hot bands because the rotational levels are really close together. So you're going to be looking at J is the rotational constant. So J0 is the ground state. You're going to be looking at J1 to 2 and 2 to 3 and 3 to 4. You're going to be going all the way up to like J25 to 26. So you'll have a lot of rotational hot bands, but all your vibrational lines will be fundamental vibrations or combinations. Let's look at the HD spreadsheet. Let me see if I can get this to come out. So the high definition workbook actually has 15 different quantum states. So, There it is. Okay. All right. Just making sure the video is good. Okay, so this one has 15 quantum states. Let me put this box at 8, like it is. On the other one. And let me shrink it down a little bit. Kind of running out of space. So 650, let's go to 800. Okay, there we go. So same fundamental, electron on an 8 angstrom wire. Here's the fundamental. These are all the hot bands. Why do we have so many hot bands? Well, because we're at 500,000 Kelvin. Okay, so now we can, let's do what we did before. Let's make it room temperature, 300. Just the fundamental. Okay, undo. Okay, so we got all of these hot bands. Let's not go so crazy. Let's do 50,000. We cool it down, and we've lost a lot of those really hot peaks. We've now got 5 or 6 peaks because we dropped the temperature 10 times. Okay, let's undo. Here's the spectral line width. So our instrument has got a really poor resolution of 50 nanometers. Okay, let's make it 40 nanometers. So right now, if you were to just collect this spectrum, all you would get would be the black curve. So you go to the UV-Vis spectrometer, you collect it, all you get is the black curve. And you look at that black curve and you say, I see 3 peaks. Right? You got a really tall peak here, a shoulder, that would be a shoulder there, and then an independent peak here by itself. Okay? And so you're like, wow, I've got 3 transitions. No, you've got hundreds, thousands of transitions. Okay, but if we cool it down, we can get rid of those hot bands and simplify the spectrum. What if we get higher resolution? What if we get a better spectrometer or tighter settings? We go to 40 nanometers. See, now that shoulder is even more pronounced, and we're seeing a second one show up. What if I go to 30 nanometers? So this would be the spectrum. You're changing the parameters of the instrument. You're making it more higher resolution, and you're getting more information. So now we have 2 definitely distinct peaks here. And now we have another shoulder on the big peak. 30, 20. It looks like the individual peaks are getting taller, but it's really the black curves coming down and the graph's auto-scaling. Okay, so the intensities of our individual transitions are not changing, but the graph is auto-scaling because this overall curve is coming down. Let's go to 10. So yeah, we're getting lots of resolved peaks, and still this little mess right here. So that's spectroscopy. Let's look at the errors, numerical errors, and this will be the last thing we do. So this is the higher definition workbook where I have 15 wave functions times with 15 wave functions. Let me go back to 15. So here's the analytical solutions in this column, going up to wave quantum state 15, and here's the numerical solutions. and look at my errors. It's 0.03%. Whereas before, with just 10 divisions, a really coarse grid, I had 3% error for the ground state. Now I have 0.03%. So that's really good. Even up to quantum state 5, I've still got less than 1% error, because this is the number of rows I have for my wave function. So for the wave function, it goes down, I think I have 100 rows. So I've gone from 10 increments to 100 increments, and I've improved the error by 2 orders of magnitude. You can still see the box. I'm doing the center derivatives. So this is the wave function page. This is the Kronecker delta page. Look at that. All the diagonals are 1, and everything that's not a diagonal is 0. The non-diagonals are any wave function times any other wave function, but the diagonal is wave function times itself. So it's normalized and orthogonal. Here's the first derivative page, here's the second derivative page, and here's the Schrodinger page. And so here's the Schrodinger equation, and you can see the matrix behind it. So all the off-diagonal elements are 0. The diagonal elements are the eigenvalues, and those are the energies for that equation. Here's the perturbed light page, so x times psi, and here's the transition dipole moment integral. And this is so beautiful because this tells us the selection rules. So right here, even with the first 15 wave functions, you see the diagonals. So what do we see here? This number right here, all of these diagonals going down, those are the fundamentals and hot bands for delta n equals plus or minus 1. So like pick this one, that's 6 up there and 7 over here. So that's either the 7 to 6 transition or the 6 to 7 transition. It doesn't matter, right? They're symmetric. Okay. And then what about this one? Let's pick this one right here. That one is 3 to 6. So that's a delta n of 3. What about this one? This is a 2 to 7. Now it's showing 0, but it's probably like in the 3rd decimal place. You know, it's non-zero. So those are our selection rules, plus or minus 1, 3, 5, etc. And then here's the simulated spectrum. And so we'll talk about how to simulate these spectra in our next lecture. Okay, so y'all have a great day.